Hello. Yes, Karthik, let's begin the today's session. Karthik, are you here online?
Yes, sir, I'm online.
Okay. So far you only have joined, but it seems others will be joined soon. Okay, so you are a UG or postgraduate student?
Yes, sir, I'm undergrad,
Okay, undergrad. Which department? Which discipline you are
mining department,
mining?
mining engineering department.
Okay. University?
No, sir, IT engineering college.
So great. You are in the
Mm.
okay. You are in undergrad. Okay. So far, that how is going your practice with the subject and the assignments you are able to do easily?
Sir, some questions are able to do. Some questions, some numericals may you may give no sir in assignments.
Okay.
In that, some difficult I may feel.
Okay. So let's begin with the numerical. You are having problem in numerical. Let's begin with the numerical first. Then
Okay, sir.
we'll see that how you are facing the difficulties in solving the numerical, and then meanwhile
Okay,
others will join and we will discuss the fundamentals for that. Okay, is it fine?
okay,
No, okay.
okay, sir.
Okay, are you having a calculator, pen and paper with you?
Yes, sir.
Okay, great. Mm, okay, so let me share my slide with you. Okay, I hope the PowerPoint presentation is visible to you. So let's no, this is not this. Wait. Let me check. There is one. Okay. So okay. So we are talking about the solar flat plate collector, correct?
Yes, sir.
Mm. So in this that in the last lecture that we read about the structure of a solar water heater as an example. So we saw that there is a absorber plate and then there is conduits taking fluid and there is thermal insulation at the bottom. At the top it is a cover. uh, Cover, we use the glass cover and we use the glazed material for covering, and the light will fall on this cover. Okay, so what will happen with any kind of body when light or heat is passing through it? There will be some losses. Is it okay? So
Yes,
yeah, so there will be some losses, and like if I see simply a cup of that tea or water, having warm water, so heat will be there will be some loss of heat from the surface and its body, correct? So likewise in this case also there will be possibility of losses. One will be from top, one will be from the side, and one will be from the bottom. Okay, so I believe that in the last lecture of the NPTEL course, so you have gone all through all these fundamentals of the losses. What we say the top loss, side loss, and bottom loss, and cumulatively we call it overall loss. Correct?
yes, sir.
Yeah. So okay, so you are facing problem in the numerical solving. So we will directly jump to first to the numerical. Let's see what problem you are facing, and then we will come back. Correct? Okay. So okay, these are all the basics for that. Yeah. So we have to calculate overall loss coefficient for a flat plate collector. You please note down these numbers. Size of the collector 1.90 meter to 0.90 meter. Spacing between plate and first glass cover. So it will be like this will be the plate, this will be the first glass cover. So this is spacing it is talking about. Then spacing between plate and second glass cover, it is 4 centimeter. This is also 4 centimeter. Then plate emissivity it has given. Glass cover emissivity, collector tilt means the inclination angle, and mean plate temperature it is given, and ambient air temperature it is given. Wind speed is given, back insulation, side insulation is given, thermal conductivity of insulation is given. You please note down these numbers. If you are done, let me know.
Yes, sir.
Okay. Okay, so please try to solve it and let me know the math, the steps, how you will solve this problem. You got you got it. The what is the problem, right?
Yes, sir.
Okay, so let me know the steps first. How you are going to solve it. So simply consider that you have to calculate overall loss coefficient. Okay. So for the overall loss coefficient, as we discussed that if this is my system, so there will be one loss from this side. So we will call it top loss. There will be one loss from this side. We will call it as side loss, and one from this side. We will call it bottom loss. Correct. So
Yes, sir.
okay. So now okay. Now we have to first solve for top losses, then side losses, and then bottom losses. Then we will do addition and we will be able to calculate the overall loss coefficient. Okay. So now let me know that how you will calculate the top loss. I'm giving you 2 minutes. You just figure out. If you have to see your notes, you just see and let me know how you will calculate the top loss. You just focus what formula you will use, what the steps you will use. No need to solve it completely numeric by numeric. Just let me know the formula and the step you will use. Let's see where you are facing the problem. Yes, hello Irshad. Um, that we are solving a problem here on overall loss coefficient calculation for a solar uh, system. Okay, so we will take this solution directly by solving the problem, and I just wanted to know the steps you will follow to solve that problem. Okay, so I'm sharing my screen. You please note down the problem, and if you will noted it, then let me know, and then let me know the steps you will follow to solve it. Correct? Is it okay, Irshad? Hello, Irshad. Are you here? Okay, so the problem to solve is okay. So you have to solve the problem that overall loss coefficient for a solar system. The figures are given for that. The size of the absorber plate is given, spacing is given. You please note down the numbers, or you may let me know how you will solve it. It's that Karthik, did you able to figure out the steps to solve the problem?
No, sir, I can't.
Okay, uh, let me check with others also. Okay, so let me take you through the steps. Okay, so whenever we are talking about the calculating overall loss coefficient, overall losses, so we have to calculate these three losses. One is side loss, one is the bottom loss, and another one is the top loss. Okay, so QT, QS, and QB are the rate at which the respective loss is uh, falling there. Okay, so once we will calculate the QB, QS, and QT, then cumulatively we can calculate the overall loss coefficient. So let's see from scratch that this generic equation we know for the rate of heat transfer. Uh, this is in terms of the rate of heat losses. L is the for overall. QL is equal to UL. U is the overall loss coefficient. Q is the rate. AP is the area of absorber plate, and temperature. TPM is average temperature of the absorber plate, and TA is the ambient. So if this is system, this is the plate. So this is the average temperature of this plate, and the ambient will be the surrounding. This will be the ambient. So, or sometime it is written that surrounding air also. Okay. So and then once we have this is the QL. For solving the QL, we need the QT, QB, and QS. Once we have the values for the QT, QB, and QS, top losses, bottom loss, and side loss rate, then we will be able to have numbers for the QL. Okay, similar to, so this is the very generic equation for the heat transfer, so that we have to keep in mind always. Heat transfer means like we are having the solar water heater system or the solar collector. So the temperature will the solar light will fall down on the collector. The temperature, ultimately what we have to get, we have to increase the temperature of the fluid or the temperature of the water, so that that water having an increased temperature we can use for our end use purpose, like in the kitchen, in the for the bathing, etc. And this is the ambient temperature, and this is the temperature of the absorber plate. So the ultimate effect is ultimate goal is to increase the temperature, and for that we are calculating the heat losses. So this is a very generic equation. So Q is equal to UA delta T. So first, that generic equation we have to keep in mind. So then when we will, this is for the overall loss coefficient. If we will be talking about the top losses, then the equation will be the QT is equal to UT, the heat loss coefficient from the top, and AP, TPM and TM. Likewise, for the bottom and for the side. So for the bottom it will become QB is equal to UB AP TPM minus TA, and for the side heat losses rate it will become US AP TPM minus TA. Okay, so now if we are talking about the heat, we will talk about the heat loss from top, bottom, and then side. So first we are talking top losses. So top losses, like this is the average temperature of the absorber plate it is given. So we said that the plate will be somewhere like this. This is the system, this is one glass cover, this is another glass cover, then this is the ambient. Okay, so TC1 is the for the one glass cover, and TC2 for the another glass cover, and TPM is the average temperature. Okay, so these are, just visualize the system, and then you will be able to solve the problem very easily. Okay, so TC1, TC2, there are two glass covers, so temperature for the respective glass covers, and then we are having the temperature, ambient temperature, and we are having one more temperature, temperature of the sky. Ambient will be the means surrounding air near the our system, and then temperature sky we are talking in a whole, we are talking about as a whole. Okay, so now we see that there are a few correlations. To calculate the, first we have to calculate the QT. Okay, so for calculating the QT, we have to calculate QT, uh, top loss coefficient. Then based on the UT we will be able to calculate the QT. Absorb of the plate will be given, but this is not given exactly. Okay, so how to calculate UT? For the UT calculation, first we need to calculate the QT. If see, there are three dedicated equation for this. QT upon AP is equal to HP C1, then SC1 to SC2, and then H omega. Then you see there is again the temperature deviation term is there. Then this is the coefficient, including the coefficient terms. Okay, so first we have to see our system. First, what are the HP C1, HC1 to SC2, and H omega. Okay, so let's visualize the system again. If this is your absorber plate, this is your first glass cover, and this is your second glass cover. Okay, so HPC1 is the convective heat transfer coefficient between the absorber plate and the first line of the cover. This one, and HC1 to HC2 will be the convective heat transfer coefficient between the first and second covers. H omega is convective heat transfer coefficient between the topmost cover, this one, and the surrounding air. So here we will be not having temperature of the air, and TC1 and TC2 is the temperature of the first glass cover and temperature of the second glass cover. T sky is the temperature of the sky, and epsilon T and epsilon C, epsilon P is also in the equation, and epsilon c. So these are the emissivity of the absorber plate for long wavelength radiation and emissivity of the covers for long wavelength radiation. Okay, so what happens that generally the heat increases due to the reflection of the long wavelength radiation. For this is uh, universal for any kind of the systems. Okay, so okay, for the top loss coefficient, I'm again taking to you through these formulas. So formula 1 that considers plate to cover 1 C1, formula 2 that considers C1 to C2, and formula 3 that considers C2 to air. Okay, so for that to solve by solving these three equations, that algebraic equations you might have solved in your mathematics. So if we need more than one correlation, we have to solve for more than one correlations. So then in that case, like we have to be same, we have to have same number of the equations also. So here three equations, and with these help of the three equation we will be able to solve for the qt, tc1 and tc2. Okay, so simply say like temperature of the absorber plate is given. For instance, you can measure also tc1 temperature of the cover plate and tc2. This you have to find out, and qt then the top heat loss coefficient, heat loss rate we have to find out. Okay, based by solving these three equations we will be able to solve for these number, but before that we have to solve for hpc1, sc1 to sc2, and h omega, the convective heat transfer coefficients. For that we have to solve. Okay, because tpm is also given, and what else, t sky will be there. So we have to solve for hp c1, sc1, sc2, and h omega. So for that there is another correlation for each of them. hpcm hp to c1 is equal to Nusselt number into k upon l. Okay, so what is the Nusselt number? Whenever we talk about the heat transfer, like there is one kettle, uh, you have kept it over a gas. Okay, so when heat will transfer from gas burner to the kettle body, first the kettle body will get warmed up, then after that the bottom layer of the fluid, the topmost bottom layer of the fluid will get warm up. So what happens in the journey, the heat transfer through conduction and convection. So the Nusselt number is the ratio of convective to conductive heat transfer at a boundary in a fluid. Okay, so Nusselt number is the your ratio of the convective and conductive heat transfer. Okay, so this is your in solids always the heat transfer occurs through conduction, and in fluid it occurs through the convection. So based on that the Nusselt number comes into picture, and K is the thermal conductivity, L is the length. So once to calculate, so the value of the K and the value of L we will be having obviously, but we have to calculate the Nusselt number. And the Nusselt number we will be able to calculate based on the Rayleigh number, and the Rayleigh number is again, it is based on the liquid spacing and the temperature difference between the interface and the inner wall of the system. We have to calculate the Nusselt number. So there is another formula for that. Nusselt number is equal to G. G is your the 9.81 meter per second will be there, and beta dash the angle, then temperature difference L cube upon uh, velocity into A epsilon. And so once you are having the temperature that for your system. So you will find these values from a correlation table. So I will suggest you here is, yeah, so I will suggest you books that which book you are following at present.
जेके सुक्ता में.
Okay, so if you will go, if you are having book in your hand, you just go at the last. There you will be having the appendix.
1 minute, sir.
Hmm. So in the exam, either these values will be given, and in practice, we will be having the book with us, so we can follow these standard tables for that.
Sir, lot of tables are there.
Okay, so lot of tables are there, na? So I will suggest you that okay, you check it later. Like what we need data for okay. So while solving this problem, we need data for the air. Okay, so if I will take how the properties of the air changes at different temperature, so there will be one table that will be showing the properties of dry air at atmospheric pressure. Okay, so you may check this later also, and you will be having this PPT also, so you can download this table from this presentation also. Okay, so uh, for a particular given temperature, uh, the density, the coefficients, the thermal conductivity, PR is the Prandtl number, the velocity of the wind, all are given. Like we say that if the temperature is if there is deviation in temperature, so in that case, obviously there will be deviation in the wind velocity also. So based on the correlations, this will be a table. Are you able to find out this table in your appendix section?
Yes, sir. I already found.
Yeah. So, so for the unknown values, you can follow this table. Okay. So, okay, like okay. So, like k is not given. L is obviously given in the form in the problem. The length between glass cover 1 to glass cover 2 and glass cover 1 to the absorber plate. So length is always given. Nusselt number we have to calculate, and k is not given. K you will be able to see that k you can find out from your that appendix table. Okay, and for what temperature you will find out the k? The temperature we have to note down the mean temperature between the absorber plate and the C1. Okay, now there is one more glitch that C1 is not given. Then how you will find out the mean temperature? So and like that, if you will having the value of C, then you will be able to find out the values for the V and the alpha also from the table. Okay, so I will take you how to find out the mean temperature. Okay, once you will be having the Rayleigh number, so you just calculate Rayleigh number into cos beta. Beta is your inclination angle. This one. Yeah, collector tilt. Beta is 20 degrees given. So this is the beta, and okay, you just use your calculator. Rayleigh number you will be having cos beta multiplied by cos beta. Then you see what value you are getting. If the value is in between 1708 and 5900, then the this formula for the Nusselt number you have to use. Again, you put the value of the Rayleigh number and cos beta here. The Nusselt number you will be able to calculate here. Okay. So then next, how to calculate, uh, how to consider the C1 and C2. So just okay, where is the problem? Okay, just see that we have given a mean plate temperature 70 degrees centigrade, and ambient temperature is 24 degrees centigrade. Okay, so let's so here we have to take trials. So in this case we have to assume the temperature. Okay, so like if the absorber plate is the 70 degrees centigrade, so we have to see that how much temperature we are going to reach. So suppose the temperature of the temperature at close to the glass cover, it is 30 degrees centigrade. So based on that we have to calculate the values for the 30 and 70. Then we have to calculate the mean temperature. So okay, so for example here I will suggest you to take the temperature C1 and C2 as, let me know where, yeah. So let's consider the temperature. You please note down temperature of C1 is 325 Kelvin and temperature of C2 is 305 Kelvin. Okay, so the all the values for the temperature will be in Kelvin. Okay, have you noted it? You just note it and
Yes, sir.
yeah, you just note it and let me know in the next session did you able to solve with that or not. Okay, so that,
Okay, sir.
yeah. Okay, then based on that you have to see, you have to take an average temperature for that. uh, Now you are having the three terms HP, HC1 and HC2. Okay, in each cases one is the HPC1, another is another is HC1 to HC2, another is H omega. This one will be HC C1 and HC2. Okay, so temperature of absorber plate 70 degrees centigrade is given to us. Convert it into Kelvin by adding the value with 273. You will get the value in Kelvin. Then you take temperature of C1 is equal to 325 and temperature of C2 is 305. 325 and C2 is 305. So for this equation you have to have a average of 70 degrees centigrade plus 273. What it will be? 70 plus 273. So it will be
325.
no 70 plus 273. It will be 343. Correct?
Yes, sir. Sorry.
Yeah, 70 degrees centigrade. The temperature of the absorber plate is given. For the plate it is given, and C1 we have assumed 325. So here to get the Nusselt number we have to check the table, and to check the table we should know the temperature. Here based on this temperature we will be checking the we will be getting the all other values. So yeah, so in this case we will take a mean temperature of the plate 343 and 325. Okay, so based on that we will get all other values from the table and we will solve it for Nusselt, first for the Rayleigh number, then for the Nusselt number. After that we will get the value for the coefficient for HP C1. And likewise we can do for the HC1 to HC2 also, the same formula we can use. The only difference is the based on the average temperature. Now the average temperature will be between the 325 and 305 when we are talking about the HC1 to HC2. So based on this all other values will be we will get different values for all others. So then the Rayleigh number and the Nusselt number will be the difference. and similarly, or else we can use that empirical formula to calculate the SC1 to SC2. Again, the value of the V we have to get it from this table. Okay, so the temperature difference we will be having, and we will get this table from this table. And again, there is H omega. H omega here we will suppose that Tc2 is our uppermost plate, and after that there will be the air. So we will be calculating the average temperature for that in between the air and the Tc2. So the suppose the T of air is the around 300 degrees, 300 Kelvin. This is 305. Then the difference will be the 5 Kelvin. So convert it into the degree centigrade, and then just check for other values in the table. And there is another correlation, you may note down it also, that temperature of the sky is the temperature of ambient minus 6. So these are the three straightforward correlations. Based on that, you can calculate. Now you will be having the values for the HPC1, SC1, 2, and H omega. So now if you are having values for this temperature, uh, then based on these values you can get the values for the exact TC1, TC2, and the QT. Area of the observer plate is given. Like if you see here in the problem statement, the length size of the absorber plate L1 into L2 is given, then area will be the 1.90 into 0.90 meter square. Okay, so once we will be having this, this was using this, we will be able to calculate the top losses. Then we have to see the bottom loss. There is one insulating plate, and the heat will be transferring to this side. So we will be having this as a bottom loss and this as a side losses. So there are if you talk about the side losses, there are simply the equations 2 L3 L1 plus L2. These are the length. L3 is from the top to the uppermost level. L1 and L2 are the length from here to glass 1 and glass 2, and Ki, these are the temperature delta T, and 2 delta S. Delta S is your thickness of the insulating material. The thickness is also given in the problem statement. Delta, this is wait. So delta S, the side insulation thickness is given. So similarly, we have to calculate for the bottom losses. Bottom loss is Ki upon delta B. So Ki thermal conductivity, and the delta B is the thickness of insulation. Okay, so once we will be having the values for the side losses, top losses, and bottom loss, so then we will be able to have the overall loss coefficient. Just we have to add these all three figures. Okay, this is the value of the Ki is given, thermal conductivity of insulation 0.05 watt per meter Kelvin. Okay, so is it clear to you now that how the steps you have to follow it? Uh, in any of the problems when heat is transferring from one side to other side, obviously, and we have to see the very first equation, is Q is equal to mcp delta T. Also we use, or Q is the heat transfer rate, where, and if you have to calculate the loss coefficient, then Q is equal to mu AP into delta T. AP is your the area of the plate. We have to consider the area of the whole system of, means the plate we are talking here, and U is the coefficient, and delta T is the temperature variation. and when we are talking the temperature variation, we have to talk temperature variation with respect to of our temperature variation in our body with respect to the temperature of the ambient temperature of the air. So this will be Tpm minus Ta. So after this is a very generic equation. Based on that, all equations are derived, and then we have to calculate the step by step the loss coefficients. So I will let's have a cross check. Just you have noted down the problem statement, right? The all these figures you have noted down. These all figures. You just calculate the uh, if you are not noted down, the thermal conductivity of insulation is 0.05 watt per meter Kelvin, and side back insulation thickness delta B is given 8 centimeter. And whenever we are solving a numerical problem, so there is thumb rule. Just always check for the units. The units should be same, like you have to convert it into meter, so it will be 0.08, and likewise you have to convert it into Kelvin. It will be uh, 70 plus 273 and 24 plus 273. uh, okay, so units at both sides uh, should be in the same format. You just note down the formula for the UB Ki upon delta B, and let me know the value for bottom loss coefficient. Did you get the number for that? So the value of the Ki, do you have the value of Ki with you?
No, sir.
Okay, so I'm just sharing the slide. So Ki is the thermal conductivity of insulation. So the value is 0.05 watt per meter Kelvin. Okay, and then
Okay, sir.
okay, then we have to calculate the bottom loss coefficient. For the bottom loss coefficient, we will see the back insulation thickness. So this will be the side part, and this will be the bottom or back side. So this thickness we are talking about. So this is the 8 centimeter. Okay. So now the formula you are having here with you for the UB is equal to Ki upon delta B. So I hope now the values for the Ki and delta B are with you. Correct?
Yes, sir.
Yeah. So let me know the what the values of Ki and delta B you are putting here.
Delta B 70 degrees given in the question.
Delta B is no again that see carefully the delta B 70 degrees centigrade is the temperature of the mean temperature of the observer plate. It is it, and delta B when we have to calculate the loss coefficient, so we have to see in that part only. So I will suggest you that whenever we are solving a problem, before solving it, first visualize the system. So for example, here we are talking about the bottom loss coefficient. So our system is this much only, and we know the formula is, so the delta B is the thickness. This is this thickness we are talking about. So this is 8 centimeter is given, and the thermal conductivity is 0.05 watt per meter Kelvin. So the thing is, the formula is Ki upon delta B. So I said that the unit should be in the same format. So this we have to convert it into meter. So we will divide it by 100. So it will be 0.08 meter. Okay, so then we will be able to calculate the thermal conductivity. We will be able to calculate the bottom heat loss coefficient. So here we will put Ki will be the 0.05 watt per meter Kelvin, and delta B is the thickness 0.08. Now solve it for these numbers. What the answer you are getting?
One minute, sir.
Yeah.
0.25.
How 0.25 you are getting? What the value of Ki you took?
0.05 by 0.2, no, sir.
No, it will be 0.05. The value will be 0.05, and the thickness is given 80 centimeter. So the 80 centimeter will be the 0.08, correct?
Okay, sir. 1 minute. 0.08. 0.625, sir.
Yes, 0.625. If we will do it round off, then 0.63 we will get. And the second thing, what will the unit for it?
Watt per Kelvin by meter.
No, see here. The formula was the Ki upon delta B.
Yes,
The
sir.
unit for the Ki is, what is the unit for the Ki? Watt per?
Watt per Kelvin.
No. Thermal conductivity will not. It will be having always the term of uh, the length, distance, watt per meter Kelvin. Okay.
Okay, sir. Okay, sir. Sorry.
So the thermal conductivity watt per meter Kelvin divided by the insulation thickness, that we converted into meter.
Meter.
Okay, so what is the thumb rule? uh, this will get multiplied by this, and if I say uh, m is the 8 centimeter, if I write it 8 or 8 by 1, both are the same things, correct? So
Yes,
like,
sir.
yeah, so likewise we will write it as m by 1. If I write it by m by 1, so what the thumb rule says, the this will get multiplied by this, and this will get multiplied by this. Okay, so what we will get the unit? Watt by meter will get multiplied by this, then meter square.
Watt per meter square into Kelvins.
Yeah, watt per meter square Kelvin.
Into
Okay,
Kelvin.
so yeah, that's why I will suggest you, whenever solving a problem, just divide this that problem into parts, as you might have read in your that fundamentals of that for that problem. And then second thing, always consider the units, and the units should be in the same format. And then whenever you are reporting your answer, the number should always be having its respective unit. Okay, so these are the basic fundamentals to solve any problem. Okay, so I believe that so you solved for the UB. Will you try it for the US, the side loss coefficient? Uh, yeah, this is the side loss coefficient. See if you are able to solve it. Side loss coefficient, the formula will be the 2 L3 L1 plus L2 Ki TPM minus TA upon 2 delta. Okay, so let me know the, have you noted down the equation?
Yes, sir, I'm noting it.
Okay, okay, let me know when you are done.
Sir, done, sir.
Okay. Okay, so just, okay, this is your problem. Then just put the values for L1, L2, L3, TPM, TA, and 2 delta S. Shall I go back to the equation?
Okay, sir.
Yeah, so let me know the values for the L1 and L2 first.
1.9 plus 0.9, sir.
Yeah, so this one, and the value for L3.
L3 not given in the question, no, sir.
Yeah, L3 is given. The L3 will be the total, the, see, it is depicted in the picture also. It is the total length. So total length will be means from plate 1 to the first glass cover, and from first glass cover to the second glass cover. So if you will go to the problem, so this is given space between the plate and first glass cover is the 4 centimeter, and the space between the plate and second glass cover is the 4 centimeter. So this is 4, this is 4, so total length will be the 8 centimeter, means 0.08 meter. Correct. Now the value for the L3 also you are having. What is the value for the Ki?
0.05.
Yeah, value for the TPM.
TPM 273 plus 70.
Hmm.
Sir,
T,
ambient temperature,
no, no, no,
sir,
please repeat the value for the TPM.
273 plus 70. It was
Yeah,
given in Celsius, so Kelvin will be taken, no, sir.
yeah, correct. And the value for the TA.
Ambient temperature, I'm not seen in the question, sir. Once you go to the slide,
Yeah,
24. 273 plus 24, sir.
yeah, so all the values, so now all the values you are having. And likewise, when solving for the values, if you are having problem for the unit, you can solve in parallelly for the units also, and then you will be able to have the value for the QS. Okay, and likewise solve for the QT then. Okay, so I believe now you will be able to solve the problem. Just divide the problems into the parts as you have read into the fundamentals in the theory, and visualize the system. Then third rule is uh, have the same unit in the same format. Then do it simply. Okay. So I believe that now you will be able to solve the problem. You can
Answer is 6.4.
answer it.
6.44.
No, no, it is not 6.44. It is not. The answer will be 0.33 watt per meter square Kelvin.
Okay, sir.
Okay, you just try to solve it and then we will discuss in the next session. Okay, solve it for the
Okay,
US
sir.
and
Okay,
solve it for the UT, then the cumulative you will get it. Okay, Karthik, thank you very much.
okay, sir.
Okay, bye.
Okay, sir.